Okay, hello everybody. I'm Chuan Weng. I'm a third-year PhD student at the University of Amsterdam. So the topic I'm going to present is rank-list truncation for large language model-based re-ranking. This work is a collaboration with Negar Arbuzada, Arvind Askari, and Mohammad Alindadi, and Martin Zarek. So here we go. So a lot of recent work use large model as text re-rankers. Not surprisingly, large model-based ranker achieve state-of-the-art ranking performance. However, large model-based rankers have poor efficiency. This is because large model have billions of parameters, leading to significant computational overhead. So they are very hard to be applied in practice. So there is an example. So if you want to rank the top 100 items for a query, if you use Flunkty5 11 billion as a large model-based re-ranker, it takes about 4 seconds on average on an H6000 GPU. I think no user had the patience to wait for 4 seconds to get the result. So the efficiency problem for large model-based ranking is severe. Now, let's take a step back and think about how we can reduce the latency. So most literature on large model-based re-ranking uses a fixed ranking cutoff to all of the queries. However, we argue that a fixed ranking cutoff might lead to a waste of computational resources, and also individual queries might need a shorter or a longer list of ranking candidates. So in this work, we explore query-specific ranking cutoffs in the context of large model-based re-ranking. So we will first look at the advantage of query-specific ranking cutoffs. And so if using query-specific ranking cutoffs is really beneficial, let's look at how to predict query-specific ranking cutoffs. So let's move on to the advantage of query-specific ranking cutoffs. So we found that query-specific ranking cutoffs improve ranking efficiency. So let's first define a notion. The notion is Oracle ranking cutoff. So for a query, an Oracle ranking cutoff is the minimum ranking cutoff that produces the highest indices at 10 value. So we could regard Oracle ranking cutoffs as ideal or effective ranking cutoffs, query-specific ranking cutoffs. So there are two plots that shows cumulative distribution function of Oracle ranking cutoffs for two pipelines. So namely BM25 plus RankLlama and RepLlama plus RankLlama. So here, RepLlama is a large language model-based density retriever, and RankLlama is a large model-based re-ranker. So what we found, so you can see, individual queries have different Oracle ranking cutoffs with a wide range. So some queries do not need ranking at all, but some queries need a ranking depth of 1,000. Especially if you look at the plot for RepLlama, you can see especially more than 20% of queries do not need re-ranking. It means that the quality of a retrieval list from RepLlama is good enough in terms of NDC at 10. If you do re-ranking, there is no improvement in terms of final ranking performance. So if you set a fixed ranking cutoff here, a deep fixed ranking cutoff will waste computational resources because a lot of queries do not need re-ranking. If you set a shallow ranking cutoff here, it will hurt ranking quality for queries that need a deeper ranking depth. Also, surprisingly, we found that query-specific ranking cutoff also improve re-ranking effectiveness. there are two plots showing re-ranking quality in terms of NDCG at 10 with respect to fixed re-ranking cutoff and the Oracle re-ranking cutoff. So we found that Oracle re-ranking cutoffs show statistically significant improvements over all of the fixed re-ranking cutoffs. Also, if you use a deep fixed re-ranking cutoff, it does not always result in improvement. Also, if you go deeper, you observe a slight decrease in re-ranking quality. So this is because if you include a large number of irrelevant documents in the re-ranking candidates, there is a high chance that the re-ranker would lift the irrelevant documents to the top of the rank list, so which is harmful for the final ranking quality. So our findings are consistent with one study published 2 years ago, which focused on BERT-based re-ranking. So in our work, we focus on larger model-based re-ranking. We found similar findings. So now we already know the importance of query-specific re-ranking cutoffs. Now let's move on to how to predict query-specific re-ranking cutoffs. So there is a research lab. The name is rank list truncation. So we think rank list truncation has the potential to solve this problem. So the task of rank list truncation is to predict how many items in the rank list should be returned. And this task optimized the truncated rank list regarding a user-defined metric, for example, F1 score. Also, this task benefits a lot of applications where reviewing returned items is expensive, for example, in the scenario of a patent or legal search. So in our work, we reproduce existing rank list truncation method in the context of large number model-based re-ranking. So, so you can see, so please look at the framework. You can see truncating the retrieval list directly translated to a decrease in re-ranking depth. So we can regard the documents in the truncated retrieval list as re-ranking candidates. And for the final target, we expect to achieve a better effectiveness and efficiency in terms of re-ranking. So this is our idea of how to predict query-specific cutoffs. Now let's look at our research questions. So we have 3 research questions. So the first is do rank list truncation method generalize to the context of a larger model-based ranking with a lexical first-stage retriever. For research question 2, we explore the situation of using learned sparse or dense first-stage retrievers, and we will take a look about how does it compare to the case of lexical retrievers. For research question 3, we explore using pre-trained larger model-based re-ranking instead of a larger model-based re-ranking. So we consider 8 rank list truncation methods, and so 3 are unsupervised and 5 are supervised. So you can see setting a fixed ranking depth is also one of the unsupervised methods. So we consider all the widely used ranking depths in the literature, 10, 20, 100, 200, and 1,000. And we consider 2 data sets, track deep learning 19 and 20. We train supervised method on deep learning 19 and test them on deep learning 20 and vice versa. Now, let's move on to the result part. So for research question 1, we want to explore the situation of using larger model-based re-ranking with a lexical retriever. So here, we use BM25 as a retriever and the rank llama as the re-ranker. So the plot shows NDCG at 10 values with respect to the average ranking cutoff. So the average ranking cutoff can be regarded as a re-ranking cost. So if the model is located in the upper left corner in the plot, it means that the model can achieve higher ranking quality with less cost. So we prefer the models located in the upper left corner in the plot. So we found that fixed ranking depth can closely approximate supervised the result of supervised rank list truncation methods, and supervised rank distribution method do not show a clear advantage over fixed re-ranking depths. And for research question 2, we consider two first retriever. One is Splitter++ and RepLlama. We still use the RankLlama as large model-based re-ranker. So we only show the plot about using Split as a retriever because we observe a similar result using RepLlama as a retriever. So we found that, please look at the gray star in the plot. There is one supervised rank distribution method. The name is MapMTCart. It shows a better NDC at a 10 score compared to a fixed ranking cutoff of 20. Unfortunately, we found that the improvement is not significant. And also, we found that a fixed ranking depth greater than 20 does not significantly improve ranking quality in terms of NDC at 10. So it means that a fixed ranking depth of 20 achieves the best effectiveness and efficiency trade-off if you use a very effective retriever. So for RQ3, we still use BM25 as first retriever, but we use a pre-trained longer model-based rankers, that is MODEL-T5. So we observed the similar findings to RQ1. So now we also let's take a look at the error analysis for supervised rank distribution methods. So the plot shows the cutoff distribution from Oracle and one rank distribution method, MTCart, because we already observed its good performance in research question 2, right? So you can see, according to the Oracle re-ranking cutoffs, around 20% of the query do not need re-ranking. So Oracle cutoffs are 0 in 20% situations. However, you can see supervised methods fail to predict a ranking cutoff of 0. So therefore, it's important to improve supervised ranking distribution methods' ability to predict when the ranking is unnecessary. So also, so please look at the plot about RepLlama plus RankLlama. You can see the model seems to perform worse when truncating RepLlama's rank retrieval list. So it seems that the model underfit for RepLlama. So it also suggests a potential need for more training data for this task. So now let's look at the takeaways for our study. First, the type of retriever makes a difference. So if you use an effective retriever, for example, Splitter++ or RepLlama, a fixed ranking depth of 20 produces an excellent effectiveness and efficiency trade-off in re-ranking. So a fixed depth greater than 20 does not significantly improve ranking quality. So as you know, previous work use a fixed depth of 200 to rank the rank retrieval list returned by RepLlama, so which leads to a waste of computational resources. And we found that the type of retriever either using large model-based, we found that the type of re-ranker either using large model-based re-ranker or pre-trained language model-based re-ranker does not appear to influence the findings. And we found that a supervised rank distribution method needed to improve their ability to predict 0, to predict when not to do re-ranking. Now let's wrap up the paper. So in this work, we provide an empirical analysis in the context of large model-based re-ranking. So we found that effective query-specific ranking depths can improve re-ranking efficiency and effectiveness. So we reproduce rank distribution method in the context of large model-based re-ranking. Last but not least, the data and the code are open sourced. For future work, we think it's valuable to explore rank distribution method for pairwise and list-wise large model-based re-rankers. Also, it's valuable to design a new rank distribution method for large model-based re-ranking. And that's it. Thanks for your attention.